that time again. Welcome to Longevity Industries' presentation of the Destiny of Manufacturing podcast. I'm your host, Dean Phillips, and I am so proud to be here today. I have with me Dr. Jason Jones from Hybrid Manufacturing Technologies, where he is the co-founder and CEO. Welcome, Jason.
Thank you, Dean. Great to be with you.
Great to have you, sir. And it's been a little while. It was back on episode 109, so our first season of the show, when we talked last officially. We've talked since then, but not officially on the air here where anybody else could hear us. So tell us right off the bat, what is your key takeaway for 5 years from now?
5 years from now, things continue to get more and more exciting. We're at the intersection of additive manufacturing and more traditional manufacturing techniques. And we just see a huge ramp up in adoption. And so if you're still wondering where your place is with that, I would say prepare over the next 5 years that your time is coming. And I would say that most manufacturers will have moved into that phase within the next 5 years.
Wow. That's excellent. I like that. Tell me a little bit. Now, you've been involved in so many things. Tell us what you've been up to since our last show as far as some of the ventures you've been involved with, obviously with Hybrid Manufacturing Technologies, but also what have you been doing in additive from the standpoint of furthering the industry?
If we look at furthering the industry, one of the things that's come out of our work with hybrid is, and just for those who are listening in, we take additive and inspection and we co-locate that often inside of CNC machines or robots or gantries. So it really kind of melds together the traditional manufacturing with the additive and digital age manufacturing techniques, digitally driven, I guess we should say, manufacturing techniques. And one of the things I'm really pleased about is that mainstream CAD/CAM companies have seen the opportunity and are now offering software CAD and CAM and even inspection technologies that address this fusion, which is really important for widespread adoption across all of the industry. And so I'm thrilled with that. We did work at ASTM. I was one of the founders of the F42 committee, for a technical committee dedicated to standards. Mm-hmm. We've done lots of work on file formats and trying to attract the CAD/CAM world. And I have to say the hybrid of the two has really given them a lot more to sink their teeth into and help them move forward.
That's really an interesting dynamic there when you think about using additive combined with subtractive and what doors that opens for a lot of people, because most people were using some form of subtractive in their manufacturing process. It just was not in one co-located environment.
Correct. Yeah, and you ask what's happened over the last few years. Obviously, everyone is very focused on parts they're making to try and make a business case. Mm-hmm. And what we've seen is as you bring together additive and subtractive, even if it's just in the same workshop, but especially when you begin to co-locate them, you start to have enterprise-wide benefits and impacts that may not be obvious when you first look at, hey, we're going to adopt this technology for this set of parts, right? And so it's been really exciting to see the way lead times can be shortened, a reduction in capital equipment. And one really strong theme that ties back to the CAD/CAM discussion is frequently we'll see people who use lots of different data systems to try and, because they use multiple manufacturers of equipment. And as they bring these together, it simplifies their data handling and gives them much better data integrity, which is key. I think over the next 5 to 10 years, all manufacturing everywhere is going to see an amazing uptake of data-enabled sensing and decisions.
You said something really interesting to me, which I hadn't really contemplated previously, because I had a conversation earlier with a manufacturer talking about how much you pay for space. What is the cost of floor space? And it was interesting that you just said, things being in one location and having, thinking about both in one machine, how much floor space that saves you when it comes to your shop, and how much that costs you by having to have two machines. So that was really interesting that you said that, because I hadn't thought about it until we were just talking a minute ago with another company, and that exact thing came up.
Well, usually dealing with overheads is assigned to somebody different than the person that's actually managing production.
True.
And so, in fact, I remember walking around a factory floor with one of our customers, and they pointed out, literally, they had a bunch of carts, wheeled carts with parts that were work in process. And they were cooling down. And I said, well, what about those? They're like, oh, we don't count that. Like, well, why don't you count it, right? It's an 8-hour cool down cycle. Why don't you count it? Oh, well, it's not active, processing time, and it just sits over there. I'm like, but what about the space? What about the, the safety and the management that goes with it? And they're like, well, we just, it's not within their scope of responsibility, and therefore they don't count it as a cost to them.
Right. Well, it's kind of interesting. You say that a few years back, now I say a few years, probably closer, more like 10 years ago or more, probably more like 20. But when we were big into offshoring tooling, that was one of the big topics, was that the purchasing agent is tasked with going out and finding the cheapest tool possible. He's not tasked with finding the cheapest tool possible that doesn't increase work in-house or didn't increase other aspects, which is what was transpiring. People were having to pay more to maintain their tools. They were not as easily maintainable. They were having to do more things with them, or they didn't even work, and they had to have them reworked to even be used. And that is exactly what you're talking about, with the scope of what somebody's responsible for impacts how efficient you are and how much you use those kinds of tools.
And we live in a time where we have to specialize, right? There's so much knowledge. We live now in a time where there's never been more availability of knowledge, and it's phenomenal. But it's also overwhelming, because no one individual can digest it and gain enough knowledge to make it actionable fast enough. And so these organizations or businesses or institutions then have to have all these experts come together and create a synergy of knowledge. And it's hard sometimes to get a global picture, even just within engineering disciplines, let alone adding all of the marketing and sales and business and, all the different skills that are required to really run a business well. So I think that it's something we need to bear in mind. We're hopeful that big data will help us all get to a more holistic picture of how all these things work and make it more intuitive and more obvious to make decisions.
Yeah. I'm hopeful for that too. Hopefully sooner than later. Tell me a little bit about, you mentioned about the more adaption or larger adaption to these 3D systems. How do you see it? In terms of how they're used with additive manufacturing, but also the ease of use. What do you see going on in those two areas?
So there's two things. And if we talk about wide scale adoption, and we're very exact in our numbers, let's isolate just to metal 3D printers for a minute. We're barely into, beyond thousands of metal printers worldwide. We're in maybe tens of thousands, but we're not in the hundreds of thousands or millions. And if we look at machine tools by comparison, the install base is millions, right? According to my figures, somewhere in the area of 350,000 machines are built a year. They often last 5 to 10 years or more. There are millions of these machines installed. So that's one of the reasons why we see hybrid as a strong adoption curve. Because if you take the additive capability and put it in even an existing machine tool, you're enabling, these machines that make everything else with that capability, and you've already got skilled operators that use them.
Sure. Yeah, because they've been running other machines that they can understand and comprehend in that same technology. So, yeah, I could see that.
Correct. And for the benefit of everybody listening, if we talk about additive manufacturing, as an umbrella term, we've got like 7 different technologies, at least 7 different sets of physics of how these processes work, at least. Mm-hmm. And so it's fair to say that, in our estimation, about half of those techniques are relevant and can be merged with something like a CNC machine. The other half are so specialized in the environments that they're required. You've got vats of resin or powder bed, and they really will maintain, from our perspective, a distinct nature. They may merge and become special purpose machines with milling capabilities as hybrids, but they're not going to look like a normal machine tool or have that capability. So that's just a little differentiation for those listening in. But we do see a large proportion of additive techniques being able to merge with existing motion platforms to become these hybrid platforms.
That's I believe the unifying theme of all of it is you have to have some motion system that's going to move whatever it is, however it is, whether you're moving things up and down or across and over. You still have to do the same thing. I used to talk that when we were using lasers, same kinds of things. The delivery system, it's still going to use some level of motion control that moves it back and forth. And you can try and find ways to do that more efficiently and faster. But when you start talking about temperature control of other things, if you're using things that are going to have to heat up materials or melt materials to whatever degree, you're going to have some level of temperature control within that. What do you see being the next level of production increases? What do you see coming down the road as far as, hey, all of a sudden we're going to go from making 50 of these parts a minute to making, or an hour, excuse me. I would love to get to 50 parts per minute, but I don't know many of the systems that get to 50 a minute.
Only very small parts, right?
That's right. It would have to be very small to get 50 per minute out of it. But what's the next level of increase coming from? Is it more in the materials, the control of the speed that we're moving at, or temperature control? What areas do you see coming down the road for us?
Additive manufacturing has always been a 3-way intersection between materials development, the platform itself, right, sort of the electromechanical solution, and software. And there are advances on all 3 of those simultaneously. When additive was new and it was focused purely on prototyping, the mechanical performance of parts was not as important as the shape that you could get to. So 3D printing is good at making complex shapes or arbitrary shapes without tooling, which is outstanding. Now that 3D printing is moving into this manufacturing era, and when we founded the F42 ASTM F42 Standards Committee. This is a technical committee to support standards. This was in 2009. We had a long debate about what to call the technology. And we called it additive manufacturing intentionally because we knew prototyping, although prototyping is making something, it doesn't have the same context or connotation as manufacturing, as in being able to reach mass markets. Mm-hmm. But we named it that because we knew that's where its growth was leading, and that's where a much larger market is. As we make that shift, we need materials that perform. And additive is in this transition phase now where, of necessity, we had to match existing material properties just to get basic adoption. So we're really using casting alloys for the most part. Mm-hmm. And from a polymer's perspective, We can use the same chemistries as you'd seen injection molding, but often it's without pressure, and therefore the part properties themselves need additional enhancements to get to the same level as what you would get with injection molding. So we've got materials that are sort of optimized for other manufacturing processes, and that materials development is accelerating the way that we can take advantage of them with additive.
Materials seem to
so
be...
That was probably a long... Oh, sorry, I was going to say that's a long-winded way of saying, as we shift to materials, right? Polymers, metals, ceramics that are optimized for being used in an additive way, we really get to dramatically accelerate how they behave.
Right. And I think there's a level of as adoption increases, as that number starts to increase, you also find that that's where you actually gain a lot of information. As the adoption increases, the information is going to increase with it. Because if we have a limited number of people using it, we have to kind of suffer those slings and arrows of doing that by ourselves. We have to do all the material research. Right. You have to have in-house chemists, in-house material specialists, and that's not making it as attractive for some people. I think that level of education makes it still a little bit challenging. And I know SME a few years back was talking about creating more databases like that system. And I think there is a need for that. But I think along with that has to come adoption. What areas, what do we do to get a greater adoption other than, yes, it's great that you go to a college and all these students are making things one-off items. What do we do to make it wider scaled as far as the adoption goes?
I think there's two sides to that story. One is that additive was born in the digital age. There was already personal computing. And as a result, if you look at a lot of the interfaces that control additive machines, they feel pretty modern, many of them. Mm-hmm. From my perspective, running machinery should be as easy as video games. I'm not saying video games are simple necessarily, but there's an intuition that comes with the controls that go with video gaming. And I think we should try to maximize that and make it feel more like that. And I think there's a lot of scope for that. There's various people doing that now, sort of gamification. But I really do mean that our future workforce, particularly if we think North America, but all over the world, if they can come from a gaming perspective into this, it'd be a lot easier. The second piece of that puzzle is unlocking design potential. Everything that's made, when you know how it's going to be made, you follow the manufacturing design rules that go with the target manufacturing process, whether it's injection molding or machining or casting or composites. There are a set of rules that allow you to make it in the most cost-effective way. And as we can spread knowledge of those rules about additive out, and we can help stakeholders who have design authority, and I'm thinking of large-scale OEMs in the aircraft and automotive and ship making and other industries, as they gain confidence in additive and know those design rules, they'll be able to optimize their solution, their parts for whatever the optimal manufacturing process is. Sometimes it will be additive. Sometimes it may be something else. But to me, it's the spread of the confidence and performance capabilities, right? We talked about materials earlier, how well they perform, but it's the knowledge of and confidence of saying, I can design it in a new way and it will perform, and therefore this becomes our most cost-effective solution.
It's interesting that you said, as far as using like somebody who knows how to run a game or play games and do those kinds of things, that it's more graphically user-friendly. I can remember when I was at a vocational high school and we were still doing tape to feed into the machines at that time. And
right.
I can remember this was just the start of computers in the 80s when things were moving in the graphical user interface, and how much that exploded the adoption of computing from staring at a screen with a C prompt with a C colon next to it, to where we took off to where I'm just clicking on something to launch it. And I noticed that kids today I'd like to use the word that they are fearless when it comes to what they're doing. They're not afraid to click on the wrong thing. They're not afraid to do things. And that level of fearlessness has a huge advantage to it, because those people that are doing that can adopt so much faster to the technology. What skills do we need to have when we're talking about decision-making and processes to make that leap? What is it that we need to do when we design our decision-making and to where there's a decision tree to be made? Hey, we need to do this and go in this direction for manufacturing, and you're going to decide to do it additively instead of in a way of a subtractive process.
For most people, making things graphical makes them easier and more intuitive. When I first started using CAD, you would commit to a CAD function or an operation where you were going to, and this was obviously in a virtual environment, extrude something or add a boss or something like that, or do a revolve. You'd commit to it, and then the computer would show you the outcome. Now CAD gives you a preview, right? So as you're setting your parameters, it'll update that boss on the fly. It'll change the shape. And so you get kind of a preview of this, and it's like, is that what you want? And then you can click OK. It's much easier and faster when you have this kind of preview and this graphical feedback. Most manufacturing equipment, and I think of pretty much anything that's CNC controlled, the majority of it still does not have enough graphical interface, in my opinion.
Mm-hmm.
To run a CNC machine or a CNC controlled tube bender or, a bunch of things like that, often you're still doing programming in some way, right? You have to know a certain syntax and type it in and know about it. It may be graphical in a CAM environment, but then when you actually get to running it, that same philosophy hasn't migrated across to how we use it. It needs to feel like a smartphone. That's my opinion.
Yeah.
And that change is underway, but the refresh rate on high, expensive capital goods is slow enough that it just is going to take some time.
I know when I look at some of these new robotics programming systems that are trying to go to a more universal system, so you can program any robot using the same interface. I think that that makes it easier for people who are trying to get into the system. And you don't have to know a whole lot of parameters. I don't need to know how much torque I'm using or how much, what the range of motion is I want to limit it to, or how fast. I don't need to know ramp up and ramp down speeds. Those can be calculated. If you look at flying a drone, you can go get a drone for roughly $100. And with almost no knowledge of how it works, how you can fly a drone, a very simple and a very basic one, but it knows how fast to do it. It knows how to adjust for anything, wind, position. It can adapt to those things. How long till we get to that point in our processes where we can take feedback on the fly and actually apply that information to our system? Do you think that's something that's within a 5-year range?
I think the beginnings of it are definitely within a 5-year range. But I also think it'll take longer than 5. Like, we'll start to be able to demonstrate it. But to use it and to mainstream it, based on refresh rates of capital expenditure stuff, it'll take a bit longer. But I absolutely agree with you. Trying to make things more universal is a fantastic thing. Your analogy about the drones, what I love now is you can tell a drone either a path you want or a result. I think that some of our manufacturing techniques are still, they're hampered by what legacy has been, all of the things in the past. And even our design now, we choose a material for a specific part. Additive makes it to where you don't have to choose one material anymore. You can choose several materials. You can make multi-material parts, and we think at some point we'll be able to define what the needs are and let a more sophisticated decision-making process decide what materials that part ends up as, or present you with several options. Here are the 3 options you could choose that would all fulfill your requirements. Maybe one would be metal, maybe another would be polymer. And then maybe there's an extra condition there, right? Temperature, use temperature or something like that helps you make that decision. Well, for a long time, we've talked about performance attributes. Then somebody has to actually decide what materials. And then somebody has to create the shapes, like design the shapes. And then somebody has to design a manufacturing process around it. And we need to do all of those in parallel because they're all interconnected and they don't have to be siloed anymore.
That's a good point.
We're starting to see now, and I'm trying to remember who said this quote in the 80s. They said, in the future, parts will be calculated, not designed. And I think that's a great description of how we're getting, the point we're getting to with some of the geometrical optimizations that we see. But we need to then add into that the multifunctionality piece, right? How do the electronics flow within that? What can you do from a microfluidics perspective? All of these disciplines that we work so hard to become specialists in have to come together somehow. And they have to come together in a more fluid, more automated way.
Yes. And I think if you look at, speaking of, and I hate to just use the drone as an analogy, but if you look at the technology that was used, you're talking millions of dollars to invest in the understanding and the back office calculations that are done within drones. If you look at what that takes now, everybody is using that same technology, the same mathematics, the same calculations to fly whatever drone it is. It doesn't make any difference. They're using, there's obviously more sophisticated sensors, there's more sophisticated systems, but the calculation aspect is, okay, if this side's flying low, you have to increase the speed of the motors on this side. Great. And I think we can get there in additive if we can start to agree upon, sort of like music was when they came out with MIDI communication. Well, they standardized on it, and it was the best for everybody involved because it made it where all of these systems could talk to each other. And since they can communicate on the same system, that makes it more possible to go ahead and explore new ideas, take information, and use it commonly across all platforms. Is that still a challenge, do you think, for most of these companies to say, yeah, let's have a common language?
It is a huge challenge. And when industries create standards bodies, right, or not create the standards bodies themselves, but create standards within a standard, organization, standards development organization, you have to have a lot of discussion across every stakeholder in the whole industry. It's a very positive and helpful process. But when it happens within additive, there are so many sets of physics that are being considered that strategically in the early days, we had to say, look, we're going to focus on standards that are umbrella style in that they do apply across all the different sets of physics. And then later will come standards that are specific to a single process category There are 7 standardized. There are some processes that are, don't quite fit the standards anymore. At the time, it pretty much housed all of them. But there's 7 or 8 or 9 basic sets of physics now. Those standards then have to be applied within those families to have total context. So it's a huge challenge because people are speaking different languages.
Right.
Even though they're all making things, once the physics changes, sometimes they even use some of the same terms in slightly different ways.
Mm-hmm.
So it is a communication challenge. And since additive, like CNC machining and forming, and it's a very broad serving from an industrial vertical standpoint, it serves every vertical. Then within an applications context, you also have translation issues. So you asked earlier what's possible within 5 years. To me, the biggest bottleneck is our mindset. And then once we can all, unify essentially and expand our vision of it, then it's a communication challenge.
Mm-hmm. What hampers us now going forward to saying we need to consider additive manufacturing when we're looking at a solution to our production problem? Is that more education that we need to do from a corporate standpoint? Is it that we need to have more additive engineers in that company, let's say? Is it more education that we just don't have enough people to supply within that? Because I know that has been a challenge, that to find good people has been a real big challenge. I think every company has experienced that. Sure. Where does the challenge lie? What's the biggest one?
Access to really great knowledge is still fragmented within the additive industry. And so some of it's imagination. I would still list imagination as probably the biggest bottleneck. People don't dare to believe that they could go as far and make as much improvement as they could. That then has to be balanced with really great information. And a lot of the types of data people look to, material performance properties after they're printed, all of that kind of thing. Right now, people are using that as competitive advantage. And so it's not widespread and known in the industry. Not like you can look up a single, data point that says, oh, if I do this treatment on this alloy, I will get this strength. Mm. That's pretty well known now across a whole bunch of alloys within a casting environment, for example. That doesn't yet exist in additive. And so it's hard to get comparison apples to apples across additive. And the reason for that really is largely because these are digital processes. Each individual voxel of every single part can be treated to some degree different. Obviously, there's intermingling effects that they affect their neighbors. But every voxel can be different. And that's a level of customization nobody's ever dealt with before.
Right.
I would argue. Composites have done a great job of starting to identify, hey, we can do, all these different weaves and all that. So they have dealt with it to some degree, and additive then takes that and goes one step beyond.
Do you think that's going to be a hindrance to adapting artificial intelligence to some of this? Is that since everything's somewhat siloed and the lack of communication internally from machine to machine to process, that limits adoption of tools like AI to quickly ramp up and improve things?
Yeah, I think it creates an opportunity where AI has an even larger opportunity to make an impact.
Okay.
And machine learning. We just have to avoid the artificial, whatever the opposite of artificial intelligence is, right? The artificial, I hate to say dumbness, but usually
ignorance, artificial ignorance.
Yeah, ignorance. I'm good with that. The other part of AI, the AI, unintended AI.
Yes.
When we feed them, it's hard sometimes to get a holistic view on all of it at the same time. And it's a learning cycle for all of us.
Right.
So we want to make sure we get great data out. But these things are coalescing. What I'm discussing this isn't me isolated in one room far away from everybody else. In general, people want to get to this solution. And the more we can implement and leverage people's knowledge and automate it, the faster we get there.
Great. And on that note, we've come to just about the end of our time, sir. How do people reach you?
They reach me at our website, hybridmanutech.com, or on LinkedIn. Feel free to reach out. Jason Jones of Hybrid Manufacturing Technology.
It's been great to have you, Dr. Jason Jones, today. It's been great to have you here on the show.
Thank you so much. Thanks, Dean.
Thanks you.